welcome grade 12s, and today we are jumping into wave, sound and light, which you did of course in grade 11, and now we're going to look at Doppler effect. I really like this section because it's something you experience all the time, but you're not always able to explain it, and it's a nice section because actually once you get the equation, this becomes easy marks in your exams, and we like that. So let's look at what some of the important terms are that you need to be able to explain and discuss. So we've got 5 here that I need you to talk about, and that's frequency, pitch, wavelength, Doppler effect, and redshift. Those are the words that are going to come up often when you're looking at problems and stuff, okay? So I'm going to give you 2 minutes to talk through those. Some of them shouldn't take you more than about 30 seconds anyway. Well, 10 seconds, even that. It's nice and quick. So I'm giving you 2 minutes, and your 2 minutes starts now. So how did you do, grade 12s? Hopefully we were okay, and you went, well, some of these terms we've been doing since grade 10, and that's exactly right. So as we go along, hopefully we'll make sure that you got them in the right definition, shall we say, for those terms, okay? So we're going to start right at the beginning, and with Doppler effect, there's a whole bunch of things we're going to need to discuss. And the thing about Doppler effect, okay, is that it affects waves. That's any wave, water, sound, light, radar, whatever. It doesn't matter what type of wave we're looking at, Doppler effect can actually be experienced by that wave, okay? So we are specifically going to be looking at sound, okay, and we're going to be looking at light. Now, within Doppler effect, we have to consider a couple of things, like, okay, so first of all here, they have waves, there we go. We have to consider the wave speed, how fast the wave is going. That plays a very, very important role. We need to consider things like, and this is important as well, what the source is, and in fact, how fast the source is going. We need to consider the observer, the person or the thing that observes the wave or can detect the wave, something like that. And then what we're really concerned about in Doppler effect is the relationship between wavelength and frequency in Doppler, and how that then relates to the speed of the wave or the speed of the source and the observer. So those are really important as we put them together. Now, with sound, the way we experience Doppler effect is by pitch, because pitch and frequency, we're going to do it again in a second, is actually really, they're related, okay? And sometimes we get a little confused with those, but they are related together. And where we use Doppler in sound is we can measure the speed of objects, we can use it to measure blood flow, we can use it to measure, to see babies, we're going to talk about that in a second as well. And then we need to be careful here because now with light, with Doppler, the way we see Doppler with light is by seeing a color change. In sound, we can hear it. With light, we have to see a color change. And then specifically what we're looking at is going to be what is known as redshift, okay? And that is shown by using an emission spectrum. I'm only going to explain very briefly what an emission spectrum is. We're going to do that again in photoelectric effect, but added to that is radar. And here I'm talking about radar guns like they use for speed trapping, okay? Because radar is a radio wave, and a radio wave is part of the electromagnetic spectrum that light falls in. But we'll get to those in a second. We're going to start off looking at sound because that's the majority of the Doppler effect we look at, and then later on we're going to look at a little bit of color and redshift, and we'll talk about that then. So, first of all, we need to remember that frequency is the number of wave fronts that pass a given point in a second. So it's how often the waves come past, okay? So the frequency together is very, very important. So frequency tells me, another way you would have done it in grade 10 possibly is defined it as the number of vibrations per second, okay? So it's the number of waves we get per second. The pitch of a sound wave is related to frequency in the following way. And this is actually really important because in Doppler questions, they will ask you about the pitch you hear, and really what they're asking you about is frequency because, okay, frequency, no, look, it's having a moment again. No, let's not do that. There we go. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. Okay, that was not a very good can't sing, we can all see this. The pitch of a sound is how high or how deep it sounds, not how loud. Often we get this confused because in Doppler, we're talking about objects that move past an observer, and yes, this loudness changes simply because the object's getting closer or further apart, further away from you, but I'm talking about the pitch, the note that you hear, okay? So ladies generally have high-pitched voices, and men generally have low-pitched voices, okay? So the pitch is what I'm talking about here with frequency. High frequency, high pitch, low frequency, low pitch, okay? Now, we need to remember, of course, that wavelength, because we need to talk about how wavelength and frequency are related, wavelength is the distance between two consecutive points in phase. So if we have a little wave, okay, you've all seen transverse waves. It's from here to here. That's my wavelength. And remember, that's lambda. That's my wavelength. That is really, really important because we're going to talk about that. Now, how we explain Doppler is when we look at the relationship between frequency and wavelength. And frequency and wavelength are inversely proportional. If I increase frequency, the wavelength decreases. If I decrease frequency, then wavelength increases. Okay, they go the opposite to each other, and that's really important. Okay, really, 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 really important. So let's get straight into what Doppler is. Now, the definition for Doppler is right here. Okay, this is my definition. It is the apparent change in frequency. Apparent change. The only way the frequency of a sound or a wave can change is if the source actually changes. But it's an apparent change, it's an observed change in frequency, and it's when there is relative motion between a source and the observer. Now, why I'm telling you relative motion is because either the source can move or the observer can move, or both, okay? We've just decided that in your curriculum or the department, our CAPS document says to us that only one will move. So either the source is going to move or the observer is going to move, okay? So what that means is let's actually look at it. So here we have, and this is the best way to do it. So we have like a police car or an ambulance, that's stationary. Let's make it an ambulance. Siren's going, it's making a noise. I'm not going to make the noise of a siren. It's national television. I'm not going to completely make an idiot out of myself. And you're standing still, and the source creates the sound, and we have our wavefronts drawn in different colors here, and the wavefronts come out at the same frequency, and none of them bunch up, none of them get further apart because the car's not moving, the person's not moving, and as the source, it's stationary. So what happens there is the frequency that we hear and the frequency of the sound given off by the ambulance, let's call it that, is the same. But if now the source starts to move, this is what happens, okay, is the wavefronts look like they bunch up on each other in front. So now here I've got the ambulance moving to the right, towards my person. Okay, so it's going in, you can see that, it's going in that direction. And what happens here is the ambulance siren makes a wave, and that wave gets produced. So that would be the first blue one that you see, okay? As that wave is traveling, the car's traveling as well. So this wave is traveling, but the ambulance is traveling in the same direction. It creates another wave because that's its frequency. But because this one is still traveling, this one's actually created a little closer than expected. And then the car moves closer, and what happens is the wave fronts in front bunch up, so they get closer together. Now, what that means for us, or whatever's detecting the wave, and we'll talk about us, is your ears interpret that because now we hear the wavefronts. So the wavefronts come, but they're coming faster onto our ear than the car was producing them because the wavelength is decreased. So we experience them faster, which means we hear a higher pitch. Okay? So the best example is racing cars. When you hear them going past the cameras, or if you're there, I hate Formula One racing, it's way too noisy for me, but you hear them go past, and that you can hear that sound as it moves past. So even when you hear police sirens, when you're in the car or the taxi, and you hear them going past you, and they increase. Yes, they get louder because they're getting closer, but the pitch, it gets higher, and then it gets lower as it goes away. Because as it comes towards you, the wavelengths bunch up on each other, and because they're bunching up on each other, the frequency increases. Now, to someone standing on this side, okay, what's happening is the wavelength, because the waves go all over, the wave comes, but now the car's moving away, and when it creates the next wave, it's further away than the first one. So now the waves are now going further and further apart. So that means that when you experience them and you hear the waves hit your ears less often, and if they hit your ears less often, the frequency decreases because the wavelength is increased. Okay, that's why it's an apparent change, and it's all about the way you experiencing the wave. And even if it's an electronic device that's monitoring the sound or registering the sound, it's the same thing. It's how it experiences it. Okay, so if the source and the observer are getting closer together, the frequency increases. If the source and the observer are getting further apart, the frequency decreases. Okay, that's really important. Now, while I'm throwing my pen around, because that's always more fun, where do we use this? I think I've messed out a page with my equation. Let's not go there. No, it's here. Okay, we'll come back to the equation in a second. So, unless it's over here, which is very possible. Oh, there's the equation. You see, it's all about reading. It's very important to read grade 12s. So, this is the equation. And I know you've seen the equation, and very, very important. That's how the equation is given to you on your information sheet. Now, FL is the observed frequency, okay, observed frequency, okay. FS is the source frequency, okay. V is the speed of sound. Now, if we're doing light or a radar, then it's the electromagnetic speed, which is 3 times 10 to the 8. Very important here, grade 12. Sound is not a constant, the speed of sound. Speed of sound can range from 330 meters per second to 343 meters per second, depending on which textbook you're using, depending on situations. They have to give you the speed of sound unless you are asked to work it out. Okay? So please, 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 please do not learn it as a specific value because it isn't. It's dependent on temperature, air density, all sorts of things. Okay? So it's not a constant. VL is the observer's or the listener's velocity, and Vs is the source's velocity. Now, from here, you will always have to make a decision how you write the equation from here, because this is very, very important. You always write it as I've just given it to you. Then, depending on how the equations given to you, what they ask you, that will determine how you manipulate this equation, okay? And we'll talk about that when we do an example. I think that's the best place to put it, because to do it now might just confuse you guys a little bit, but you've got to remember that coming towards each other, increased velocity, going away from each other, decreased velocity. The nice thing is this, oh look, it's doing its own thing, this is given to you, and you always start from there. I know mathematically it's incorrect for those of you that are very strong mathematically, and you go, no, I can't write an equation with pluses and minuses in. Doesn't matter. You do what you need to get the marks for this, okay? You make a choice after this when you do your substitution as to what happens, and you get rid of the plus and the minuses. Okay, so I'm not going to go, because I think we've done it quite a bit already. I'm not going to go into the applications. I'm going to do that in the next section. So we're going to take a short break, and then we'll do the applications. Okay, so I'll see you in a little bit. Welcome back, grade 12s. So now let's look at a couple of applications. And the nice thing about applications is they're probably just going to ask you to name it. I hope they might ask you to explain a little bit. But what an application means is how do we use this Doppler effect in everyday life. Now, the first one is what is known as Doppler flow meters. And these are used to measure blood flow, okay, in patients, and it can measure blood flow in veins, and it can also measure blood flow in a person's heart. And the thing about this is what it does is, and I've got a really nice picture for you, is the blood is flowing, as you can see, from left to right, and the wave gets an ultrasound wave, so it's a wave you can't hear, all right, so you can't hear it as it's working, gets sent out by the transmitter, and what happens is that that wave then bounces off the blood vessels or the walls of the blood, the veins and those sort of things, bounces, well, the blood vessels is what we're looking at because we're looking at the flow of the blood. So it bounces off the blood vessels and it echoes back into the receiver. Okay, so you see this is the wave that gets given in, and then it echoes back into the receiver. The receiver then takes the change in frequency and can use that to calculate how fast the blood's moving. Because if the blood was stationary, then the received wavelength would be exactly the same as the transmitted wavelength. Okay, but the blood's flown. And that way, doctors can see whether somebody has constricted veins, whether there's a problem, and all of that. They do the same when they're measuring, when they're looking at people's hearts for before they do surgery. If they think somebody needs surgery in their hearts, they go and they use it to measure the valves and that sort of thing. Okay, so that's the first thing. And then the next thing is ultrasound machines. Now, ultrasound machines are, most ladies will go through using an ultrasound at some stage, because when you're pregnant, how do they see the baby? They look through an ultrasound, okay, and they use sound. Now, we use sound and not x-rays because it's less dangerous. So it doesn't hurt the baby. It's the same concept that a transmitter gives out waves. Those waves bounce back up into the receiver. The receiver takes the waves that it receives in the frequency, and then with a whole bunch of computerized thingy-majiggy-wiggies in the middle, we don't need to know how that works, it creates a beautiful picture of the baby. Okay, so ladies and gentlemen, one day when you are going to become a daddy, you will see those as well. Okay, so it's actually really, it's a nice thing. It's a good, easy way to do things. Okay, and it's nice and safe. Okay, another one which I didn't actually put in, which I shouldn't, are radar speed guns. Like I said, for speed traps, bad if you don't follow the speed limit. Yeah, they've got me a couple of times. Don't tell anyone. Shh, it's between you and me. So radar speed guns, they use radio waves, okay? And they can measure how fast you're going by, how quickly, well, what the frequency is of the wave that gets echoed back. Okay, so that's all well and good. We need to do a problem because that's what this is about, okay? So let's look at the first problem. And they say to you, during an experiment to determine the speed of sound. So I already know where I'm going with this. They want us to determine the speed of sound. Learners are given a siren that sounds a single note of frequency 426 hertz. If you are a musician of any kind, you might be able to tell me what note that is. I don't know. Okay. But I have to be honest, this would be the sort of experiment that would drive me mad. But anyway, so the point is that my source is emitting a frequency of 426 hertz, okay? They attach it to a remote-controlled car, move it at a constant speed past a stationary tape recorder. So what they're telling me now is the tape recorder is stationary, so my listener is not going anywhere, yay, but my source is, okay? So the source is moving, we don't know what that is yet. And they tell us to ignore the effects of friction. Great, we like that. And then the tape recorder records the sound of the siren. And then what they would do is they go afterwards and they go and analyze how the frequency changed. Okay, so we know what the frequency of the source is. We know what the listener's velocity was. So let's look at the questions, okay? And I'm going to give you a couple of minutes. So the first one is you've got to name the effect which explains this observation. I'm not going to give you any time to do that one because we all know that, okay? That's the Doppler effect because that's what they're not asking you, be careful here with this question. They just said name the effect, don't explain it, just name it. Now, in one of the trials, the speed of the remote-controlled car was noted as 31 kilometers per hour. The two notes from the siren recorded, one with a frequency of 437, the other note with a frequency lower, it should say lower, than 426. Okay, so there's 3 questions there for you to do. I'm going to give you 2 minutes to do them. Okay, we had all the information on the last page, so I'm going to give you 2 minutes and you're going to start now. How are we doing, grade 12s? Hopefully we didn't get stuck on the first one with the conversion of kilometers per hour to meters per second, but we'll be okay. So let's have a look at where we're going. Okay, so we've already established that this was the Doppler effect, so we're going to go here. I already said that earlier. This is Doppler effect. Doppler effect. Now, when it comes to converting, and this is just something you've got to keep at the back of your mind, I want to show you how we do it. So 31 kilometers per hour means it's 31 kilometers in 1 hour. Okay, so now watch what we're going to do. To change kilometers to meters, we times by 1,000. So we're going to go 31 times by 1,000. That's going to change this into meters. To get it into seconds, remember 1 hour is 60 minutes and each minute is 60 seconds. So we times it like that. That gets it to seconds. So in other words, I'm going to times by 1,000, divide by 3,600, and we get 8,61 meters per second. But in an exam, we actually don't need to see this calculation. So we're going to write a little note for ourselves, and we're going to go, actually, this to convert kilometers per hour to meters per second, okay, you divide, it's a little bit of a trick, by 3.6. Just divide by 3.6. It's the same as what I've done there. If we're going, and you shouldn't be asked this, but if we do, meters per second, so this gives you meters per second. If I want to go meters per second to kilometers per hour, I times by 3.6. It's just the opposite. Okay, it's just a little trick, keep it in the back of your mind. Now, they ask you to determine the speed of sound in air. Be careful here because of the information that was given. Okay, that should say lower. Now, I was given the frequency here, I was given a frequency here, and I'm given a velocity. You're not going to use two equations. You only need to use one. The second frequency they gave you, they just said it's lower than 426. They did not tell you what it is. So we're going to have to use the 437, the higher frequency, okay? So this is what we know. The frequency of that the listener observes was, where is it, 437, okay, hertz. The frequency of the source was 426. The listener isn't moving, and the source is going at 8,61 meters per second. That's why they made you work it out. Now this is about using the equation. So I know I need to use the Doppler equation, and it says to us that the listener is speed of sound plus or minus the listener's velocity plus or minus sources over the source. Now in the substitution, this is where we make a decision about the plus or minus. So we know that this is going to be 436. Okay, so watch how I'm going to put this in. The source is, 426. The listener wasn't moving. Okay, so I ignore the top end, so I don't have to plus anything there. So I've just got the speed of sound at the top. Now I'm going to have the speed here, and this is 8,61. Now we make a decision as to whether we plus or minus. The 426 must become a bigger number. In order for it to become a bigger number, the number in the bracket must be bigger than 1. The only way that can happen is if the number at the bottom of the fraction is smaller than the number at the top. So I'm minusing the 8,61. Now it's a maths problem, okay? Because now I know I'm going to get a number bigger than 1 in the bracket, times it by 4,26, I get 4,36, 436. Or is it 437? Let's go look. Always important to write it down properly. It's 437. Okay, I'm pretty sure someone was screaming at the TV, and you're probably a little bit like my learners, and now there's no evidence that I ever put 436. Now, it's a maths problem. How you solve the maths from here is up to you. I'm a little bit lazy when it comes to this. Well, I like to find the easy way around. So I'm gonna go 437. I'm going to take the bottom of my fraction out, okay, equal, and this becomes 426V. Then I'm going to divide both sides by 437. Okay, because now that gives me a decent answer. Well, it depends on which way well, that's one way to do it, I suppose. And then, in fact, that's not how I did it in my memo. I don't know what I was thinking. Let's not do it that way. Let's multiply it in. Can you see it doesn't actually matter? I just want to show you another way. So we multiply the 437 in. So we're going to have 437V minus 3,762,57 equals 426V. I like to get rid of fractions as quickly as possible. I don't like fractions. Okay, then I'm going to take the 426 over that side. I'm going to take that over to that side. That means 11V is 3762,57. We divide both sides by 11, and look here. 342,05, close enough. Okay, now it's not 343 because obviously temperature, whatever the case may be, but 342, good enough number. We're happy with that, okay? But really, to go from, to go from the substitution, so you would actually probably get 3 marks for that part. To get to the final answer would only give you 1 more mark. If you're going to struggle and it's going to take you another 10 minutes to solve this, leave it. You don't need that V. Leave space, go back to it when you have time, but don't get yourself into a whole big flap because you can't solve for V. Okay, that's really important. Now, the last question said, give a reason, really, I keep doing this, give a reason why the observed frequencies are higher and lower than the frequency. Now here, this is about being able to tell me, for example, that the higher frequency, so the higher frequency was because the source was moving towards the observer. Okay, so the source, let's make it an S, the source was moving towards the observer. Okay, observer. Did I spell that right? I did. Like I said to some of my grade 10s today, I probably need a little bit more sleep, but don't tell anyone. Okay, now, the lower frequency is because the source, okay, was moving, let's do that, away from the observer. So what are they looking for? Higher, towards, lower, away. It's as simple as that. That's all they want. Okay? Hopefully we did that. We are going to take a short break, and then we're going to look at redshift and one more question. So I'll see you in a couple of minutes. Welcome back, grade 12s. We're going to do one little extra piece on theory, and then we're going to do one more question. Okay? So remember that Doppler affects any wave. So now we're going to talk about how Doppler affects light. And in the visible light spectrum, you have to remember that red light has the longest wavelength, red light, longest wavelength, lowest frequency. Violet, which is on the blue end of the spectrum, has the shortest wavelength, highest frequency. Okay, now why that is important is because when we look at distant stars, when astronomers are looking at the galaxies and they're looking at distant stars, we get what is known as an emission spectrum, where they are looking at the gases that the stars are produced, and the Earth acts as a cold shield, and they put it through a diffraction grating, same sort of thing as we did last year in grade 11, and that produces these beautiful emission spectrums, okay, which I'm going to show you in a second. Now, I'll show you one now. So these emission spectrums look something like that, where you get these beautiful colors and then you get these dark lines in between because certain wavelengths are being absorbed by the gases that are present in the stars, okay? And it's the elements, and we know from working with those elements on Earth what those spectrums should look like. Now, as they watch these stars, they get and from knowing our own sun and everything we know what the spectrum should look like. So for example, and that's like this one here, okay, at the bottom of my picture. But as they look at distant galaxies and stars, the spectrum, these absorption lines shift, okay, so they move. And if you look, as we go up on the page, you can see that this line here is shifting more to the right as it goes along. Okay, that means it's getting red shifted. It's shifting towards the red end of the spectrum. Same with this one. You see that's going there, that's there, that's there. In fact, it's not even on the last one. There's that one, there's that one, there's that one, and there's that one. Can you see they're all moving? It's the same pattern, but it's moving to the red side of the spectrum, which means it's moving towards the wavelength with the lowest frequency, okay, the longest wavelength. That tells me that if that is the source of the light that we're watching, it's moving away from me, because we're stationary, relative, okay, we have to have a stationary part, so it's moving away from me, so it's red shifting, okay, and that actually gives me the definition for redshift. It is a shift in the spectra of distant galaxies towards longer wavelengths, toward the red end of the spectrum. Now, why is this important? And this is going to come up. This is the question they're going to ask you. What does this mean for us? This means this is evidence. It is not proof. It is evidence of the Big Bang. What it means is it suggests to us that the universe is expanding, that as we look at the stars around us, our universe is getting further and further apart. And what scientists do is they go, well, if it's going further and further apart from us, then it must have come from somewhere. And if we reverse it, it must have come from a single spot, which is the Big Bang, the whole thing of the universe starting with a big nuclear explosion, essentially. We're not going to worry about it. The point is it suggests to us that our universe is expanding. And it is evidence of the Big Bang. It is not proof. Okay, so you can't say it proves the Big Bang theory, because it doesn't. It gives evidence towards it. Okay, and that's about all they're going to ask you when it comes to redshift. There's not much they can ask you that, and atomic emission spectrums will come up with photoelectric effects. So, let's do a question. I love this question because it's got a little bit of a echo thingy to it. It's great. Okay, so here we go. Says to us, dolphins use ultrasound to scan their environment. They're very clever animals. When a dolphin is 100 meters from a rock, it emits ultrasound waves of frequency 250 kilohertz. Okay, be careful here, kilohertz, while swimming at 20 meters per second towards the rock. Assume, now watch here, the speed of sound in water is 1,500. You're looking at water. They want you to do a couple of things. They say to you, calculate the speed of the sound waves detected by a detector on the rock. So what is the frequency observed? When the dolphin is 50 meters from the rock, another ultrasound wave of 250 kilohertz is emitted. How will the frequency of the detected sound wave compare with the answer? Such an important question. So I'm going to give you 2 minutes, and we're going to see if you can complete this. So you've got 2 minutes, grade 12s. Your time starts now. welcome. Well, I'm not saying welcome back. I'm the one who went away. So welcome back to me. Anyway, so grade 12s. Oh, I'm doing well today. Grade 12s, hopefully we did okay. Let's see how we did. So we've got our question which says a dolphin is 100 meters from the rock, emits a wave frequency 250 kilohertz while swimming, assume the speed of sound. So the first thing they ask us to do is to calculate the frequency of the sound waves detected by the detector. So what we have here is the frequency of the source is 250 kilohertz. Now remember, we can't work in kilohertz. That means we times by 1,000. So it's 250, and I like to work in scientific notation. So we times by 10 to the 3. That's times by 1,000 hertz. The source is moving at 20 meters per second. They tell me that the speed of sound for this one is 1,500 meters per second. The detector is the rock. On a rock, the rock is going to be stationary. Okay, so we know that the listener or the observed velocity is 0. So they want what is the observed frequency. So we go, fine, I know, I'm looking at Doppler. So now we say to ourselves, well, how do I calculate Doppler? And of course, to calculate Doppler, we need to use our wonderful equation. So we go, observed frequency is the speed of sound plus or minus the observer or listener's velocity divided by the speed of sound plus or minus the source's velocity, and we have the frequency of the source. Now we want the listener's frequency, so that's what I'm going to work out on this one. So I'm just going to go over here, and so we go, the listener wasn't moving, so that's 0, VL is 0, which means the top of my line is going to be 1,500. I know that that's 1,500, and I have to either plus or minus the source's velocity, which is 20. We'll come back to what we're going to do with that in a second. And my source's frequency was 250 times 10 to the 3. Now we say to ourselves, okay, the dolphin was moving towards the rock. If it's going towards the rock, my frequency must increase. So I must have an answer bigger than 250,000. So now that means inside my bracket, my answer in my bracket must be bigger than 1. So I must divide 1,500 by a number smaller than 1,500. So I'm going to minus. Okay, so I'm actually going 1,500 divided by 1,480. I times it by my frequency that we got, and this is what we get. 253,38 times 10 to the 3 hertz. An increase, that's exactly what we expected. We're happy. Okay, great, we like that. It's really just about deciding where we want to go. Then they asked you, this is such an important question. They say to you, when the dolphin is 50 meters from the rock, another ultrasound wave goes out, how will the frequency detected by the wave change? Now, for a lot of you, your automatic answer is going to be, it's going to increase. And then if I asked you why, you're going to say, because it's closer. Then I'm going to say to you, but if we look at our equation, did we ever in that equation, when we look at it, remember this is the equation that we're using, this equation never, ever considers the distance. It's got nothing to do with distance. It's all to do with velocity. So if the dolphin at 50 meters away from the rock is moving at the same speed, so he's not accelerating, he's not changing, he's not getting faster or slower, if he's moving at the same velocity, so he's still moving at 20, the detector will hear the same sound. It'll have the same frequency, okay? Because it's all about the velocity. It's not about the distance. So when we answer this question, all right, we first got to say, well, what happens? Well, is it going to be higher, lower than, or remains the same? Well, it's going to remain the same. Okay, that's very important. And when we explain our answer, okay, this is what we wanted. The frequency detected, now watch here, is independent of distance. okay? In other words, distance doesn't matter. All you can tell me is only dependent, so depends on and you can say relative velocity or speed listener or observer, either way. Okay? That is so, so important that you get that it has absolutely nothing to do with distance. It's one of those things that they tend to like sneak in to try and confuse you. Okay, so just be careful with those for me, all right? Now, added to this, I want to add one quick little thing in where we get this. One of the things they like to ask you is you have a person sitting in a train going along, and you have a person on the platform observing the train come past, and they'll ask you things about what the observer on the platform hears as the train comes towards them, as the train goes away, or the person in the car, whatever the case may be. And then they say to you, what would be the frequency of the sound observed by the person in the train or in the car? And often, because of where it sits in the question, you'll go, oh, it's going to be higher than or equal or lower than, and you go because it's moving towards, it's moving away, but you've got the wrong opposite, you're going from the wrong point of view. If somebody is moving with the source, there's no relative motion between them and the source. If there's no relative motion, the velocity remains constant. So even if, for example, you're traveling on the highway, you hear cars screaming past you and you can hear the difference in the sound, but if you're driving next to somebody, next to a car that's going at exactly the same velocity as you, and or a police car, and its sirens are going and you're going the same velocity as the police car, the velocity you're going to hear, the frequency you're going to hear is the same as the frequency that's going to be given off by the police car. Because there's no relative motion. You're moving at exactly the same pace. If the police car now decides to shoot off and gets faster, now it's moving away from you, you're going to hear the sound get lower. Okay, one other thing. This has come up in questions, is they sometimes ask you, you have a police car with the siren going off and it moves away from you, so you know the sound is going to change, and then they ask you about whether you observe any change in the color of the siren. The answer there is no. I know I've told you about redshift, but remember, you only see that shift if the velocity, the motion's velocity is in the same sort of order. It's relatively close to the speed of the sound, of the wave that we're looking at. We can't go anywhere near the speed of light on Earth, 3 times 10 to the 8, not a chance. So unless the car has turned into a spaceship, okay, you're not going to see a change in the color of the light. That's really, really important. We don't move relatively fast enough. We see it with the universe and the galaxies because they are moving fast enough. Absolutely moving fast enough. Okay, so grade 12s. We are done for today. We're going to do rates next. Yay! Next week's going to be so much fun. Okay, so done with Doppler. Practice, practice, practice. Learn the Doppler Effect definition. You are going to get asked it. And that's all I have for today, and I'll see you next time.